And so main collaborator is Hiroki Nagakura. He's in N3AS. So first of all, quark supernovae occur at the end of chemical evolution of massive stars. And after that, a neutron star or a black hole is formed. And so recently, we can observe gravitational waves from neutron star merger. And so, as you know, the gravitational waves from neutron star merger can constrain neutron star equations of state. So from this slide is from recently Sotani-san's work. So from gravitational waves from neutron star merger, we can constrain on neutron star equation of state. So this black line shows the constraint from GW 1708-17. And so for X-ray observation also constrain. So this neutron star equation of state, basically high density part is constrained by neutron star observations. And so terrestrial experiments of nuclei also constrain the equation of state at low density part. For example, so recently, Plex2, they measure neutron skin of heavy nuclei, and they constrain this low density part of neutron star equation of state. Of course, there is ambiguity in these analysis, but so both neutron star observation and terrestrial experiment constrain on neutron star matter equations of state. But so neutron star equation of state is one aspect of equation of state of nuclear matter, especially in core collapse supernovae and also in neutron star merger. So temperature become high and protons and neutrons balance are not in beta equilibrium. So in neutron star matter, so the nuclear matter is in beta equilibrium, but so in neutron star merger and in core collapse supernovae, the protons and neutrons are not in beta equilibrium. So in that sense, we require more information about nuclear matter. And so the core collapse supernovae is very energetic event, and the kinetic energy of ejector is 10 to 51 L, and neutrino energy correspond to 10 to 53 L. And they also emit gravitational waves. And so they synthesize heavy elements. And we can check the nuclear physics by using this event. So I will explain the scenario of core collapse supernovae in brief. So after the chemical evolution of massive star, this onion-like structure is formed. And central region has the iron group core. And this core collapses to proto-neutron star. A part of the iron group core becomes a proto-neutron star. It takes about 100 or 200 milliseconds. And when the central density reaches about 10 to 11 or 10 to 12 grams per cubic centimeter, neutrinos start to be trapped, and neutron sphere is formed. And after the formation of a proto-neutron star, shock waves are generated. And this shock wave expands. So it takes about 1 second for shock wave reach the outer boundary of iron group core. And so the neutrinos emitted from proto-neutron star hit the matter around the shock wave and assist the shock expanding. This is neutron heating mechanism. And this is the promising scenario of core collapse supernova explosion. And it takes about 1 day to blow up the outer envelopes. And so I'll talk about the supernova matter. So during quark collapse stage, so heavy nuclei show up. First, iron group nuclei are dominant, but so during quark collapse stage, the heavier nuclei can be formed. And they are in nuclear statistical equilibrium. So temperature becomes high and all nuclear reactions are in equilibrium. And the chemical potential of all nuclei can be expressed as this. So, and after the bounce, protoneutron star is formed. Protoneutron star is a kind of one giant nucleus. So they are interacting, they are strongly interacting. And so shocked matter is made of protons and neutrons and light nuclei. So I will show the detail later. So, and so anyway, most part of supernova simulation is made of inhomogeneous nuclear matter. This is one of my messages. So homogeneous nuclear matter appear only in protoneutron star. The other part is made of mixture of various nuclei. And electrons and photons are so uniformly distributed, and they can be calculated easily. So electrons are just ideal fermions, and photons are ideal bosons. And neutrinos are not always in equilibrium, and we have to solve Boltzmann equations for neutrinos. And this is so one supernova simulations. So in supernova simulation, we have to solve hydrodynamics of supernova matter in 3 dimensions. In addition, we have to solve neutron transport. So we have to calculate the time evolution of neutrino distribution in 3D and 3D momentum spaces. This is 2D simulation, so we need any approximation at present. So there is no complete supernova simulation without any approximations. And this simulation is based on our equations of state, and I will show later that I will discuss the result of this simulation. And this is the animation of so neutrino and matter motion around protoneutron stars. So to solve these, to perform these supernova simulations, we require microphysics input. One is equations of state. So, and to construct new equation of say EOS, we need basically 2 information. One is the nuclear interaction model. So scheme type interaction or relativistic infield theory or chiral effective theory. So we need any interaction model. So the interaction model is basically important to determine stiffness of the matter and or entropy of matter. And so we need nuclear model to calculate clustered matter. So to calculate inhomogeneous nuclear matter, we need some nuclear model. For example, compressible liquid drop model in LSEOS and Thomas Fermi model in Shun STOS-EOS. And recently, statistical NSE model is a trend. And in addition to equation of state, we need data of neutrino interaction rate. For example, electron capture on heavy nuclei. By using these data of microphysics, we can perform supernova simulation. So weak interaction rate determines how many neutrinos are emitted and absorbed and scattered. So around protoneutron star, the matter motion and neutron motion are coupled because neutrinos are trapped. But so our neutron sphere, neutrino can escape. This is simulation by Nagakura-san. And so this is the current list of data table of supernova equation state. So there are many equation state now. So about 10 years ago, we have only 2 equation state. One is famous LS-EOS. So this EOS is based on scheme type interaction. And so the other is Thomas Fermi STOS EOS. This EOS is based on relativistic mean field with TM1 parameter set for nuclear interaction. And the nuclear model is Thomas Fermi approximation. And recently, Togashi-san constructed new equation state based on variational methods to nuclear interaction potential based on nucleon-nucleon scattering data. And this is one of the new equation state. And regarding nuclear model, so NSE model is a trend. So in single nuclear star approximation, so mixture of various nuclei is represented by a single nucleus with average neutron and proton numbers. But so recently we solved mixture of various nuclei. So we consider all nuclei in equations of state. And Matthias Hempel EOS is maybe the most famous one. So he constructed some equations of state. And our group also constructed EOS. And today I will introduce some results based on FT EOS. So nuclear interaction model is variational method provided by Togashi-san, and nuclear model is one NSE model. And so recently, so many groups published various equations of state. And so in this year, so Steiner's group also constructed new equation state. And so there is a hybrid, so there are hybrid EOSs. So low density part is calculated by nuclear statistical equilibrium, and high density part is calculated by SNA EOS. This is one approach to construct supernova equations of state. Anyway, there are many equations of state, and so our group use this FTEOS now. And so I will discuss nuclei in quark supernovae and some dynamical conditions in these supernova simulations. So we assume axial symmetry, so we perform just 2D supernova simulations by using FTEOS, so NSE and variational method EOS. And the progenitor is 11.2 solar mass. And this is initial condition of quark supernovae. So at the initial phase, temperature is not so high. And so they are basically iron group nuclei, and so they are not neutron rich. And core collapse start, and this is the bounce phase profile. So here is the center of a neutron star, and density and temperature is high. And so here is neutron sphere. So just above neutron sphere, huge neutrinos are emitted, and charge fraction are greatly changed. from iron group nuclei, so from about 0.4 to 0.3. This is the profile of at core bonds. And inside neutron sphere, the charge fraction are not changed greatly. And after shockwave formation, shocked matter become high temperature. Shocked matter become hot, and temperature is increased. And so here is shockwave, and at the surface of protoneutron star, accretion matter is compressed and temperature become high. This is profile of shocked matter in shock revival phase. And in 2D or in 3D simulation, the shockwave is deformed and there are various profiles. So the temperature and density and charge fraction depends on the angle, the polar angle. And so there are various temperature and density and charge fractions. And so this is overplot. So initial phase and during core collapse phase, the temperature is not so high and heavy nuclei can survive. But after shockwave formation, temperature become high, and so these heavy nuclei are dissolved to light clustered matter, protons and neutrons, and deuterons and alpha particles. And after the shockwave formations, temperature increase and neutronization bursts reduce the proton fractions, and the shocked matter become very neutron rich. Anyway, so there are various thermodynamical conditions in core collapse supernovae. So this is why we need more information about nuclear matter other than neutron star matter. So temperature is high, and so various charge fractions are given in supernova simulations. So I will introduce nuclei in core collapse supernova simulations. This is mass fraction during core collapse phase, mass fraction at center of collapsing core. So first, iron group nuclei are dominant, but as the density increases, dense electrons reduce Coulomb repulsion among protons in nuclei, and heavy nuclei can be formed. And system become neutron rich, and neutron chemical potential is larger than proton chemical potential, and neutron rich nuclei can be formed. So in core collapse phase, heavy neutron rich nuclei are formed. Of course, these huge nuclei are not so important. So the huge nuclei can be formed after neutron sphere formation. And important nuclei is around here. So medium mass neutron rich nuclei are very important because they determine the amount of neutron emissions. And so of course the results are very sensitive to NSE model. I will skip the detail, but in these calculations, we require some information. So first, mass data, experimental or theoretical mass data, and so nuclear interaction. So nuclear interaction are required to calculate drift nucleons or some bulk property of nuclei, and nuclear excitation model. And recently, I showed that this NSE result is sensitive to nuclear excitation model. So this is one of the ambiguity in this calculation. So, and this is just one example. And so important nuclei are them. So huge the nuclei inside red line show up in quark-collapse supernovae, and so dash dotted line shows the average proton and neutron number in quark collapse phase, center of collapsing core. And important nuclei are them. So because they appear just before neutrino sphere formation. And of course, the detail depends on the model of nuclear excitation, but in any model, so nuclei around zinc 80 show up. And maybe these nuclei are very important during quark collapse phase. And so in our simulation, we use some weak interaction data, electron capture rate data provided by some groups. But so for important nuclei, we have no data. And we use just simple analytical formula provided by Kanke. So at present, we need more information about electron capture rate of them. So, and electron capture rate of them are very important, and they are not calculated at present. So I'll introduce the impact of electron capture rate. So if electron capture rate of such heavy nuclei are high, the leptons become fewer during core collapse phase. So huge neutrinos are emitted from collapsing core, and lepton degenerate pressure becomes small. And the mass of protoneutron star becomes small. And the energy of shockwave becomes weak. And the radius of shockwave becomes small. So shock energy becomes weak if electron capture rate is high. In addition, its inverse reaction rate is also high, and neutrino sphere becomes large. So neutrino interaction rate, so neutrino absorption rate is also increased. And so neutron sphere becomes large. So as a result, the amount of neutronization burst becomes small. So peak luminosity is decreased if electron capture rate is high. Basically, the amount of neutrinos emitted via neutronization burst depends on the mass between shock radius and neutrino sphere. And if electron capture rate is high, the shock radius becomes small, and the radius of neutrino sphere becomes large, and emitted neutrinos become small. Anyway, so this electron capture rate of these medium mass neutron-rich nuclei are very important, and we have no sophisticated calculation. Of course, so many groups are discussing about electron capture rate of these medium mass neutron-rich nuclei, like zinc 80 or nickel 78. So finally, I will introduce the nuclei in shock revival phase. So after shock wave formation and shock heating, increase the temperature of shocked matter, and shocked matter is made of protons and neutrons and some light clusters. And so around shock wave, alpha particles are dominant. But so weak interaction of alpha particle is not so important because alpha particle is very stable and their weak interaction rate is not so high. But so deuterons are very important. So the existence of deuterons reduces the mass fraction of protons and neutrons. So weak rate are decreased. In addition, the weak interaction of deuterons themselves also affect shock dynamics. So some work showed the impact of deuterons and tritons. So especially deuterons may be important in supernova simulations. So finally, I will summarize the impact of equation state on supernova simulation. There are many works about EOS dependence of core-collapse supernovae. But it is famous that soft EOS is positive for successful explosion. So soft EOS gives compact protoneutron star, and so neutrino heating is increased and shock wave become large. So very roughly speaking, soft EOS is better for successful supernova explosion or shock revival. And so some other work show so nuclear model is also influential on the result of shock wave. This is figure from Swasan. And so Swasan compare 3 equation state in 2D supernova simulation. And red line shows soft LS EOS incompressibility parameter is about 180. And green line correspond to stiff LS EOS. And so gray line correspond to Shun EOS, STOS EOS. And the 3 line correspond to maximum and average and minimum radius of shock waves. And the difference between LS EOS are not so large. But so if we change nuclear model, so the results are greatly changed. So STOS does not show the explosion. And some other work show, so for example, Matthias Hempel performed more systematical comparison. And so they show the difference arising from nuclear model is larger than the difference arising from nuclear interaction model. So anyway, nuclear model is also important for supernova simulations. And recently some group shows what is the key parameter in supernova simulation. Basically, these effective mass and entropy density are related to nuclear interaction model. They change some nuclear interaction and they show some key parameter for supernova simulation. And so effective mass and entropy densities may be key parameters. So for example, incompressibility parameter K may not be so important for supernova explosion. And so these effective mass and entropy density are key parameter in supernova explosion. Of course, they may be related to each other. So we need to investigate further. Okay, I will summarize my talk. And the core-collapse supernovae greatly depends on the equation state and weak interaction rate. And so nuclear model and nuclear interactions model are required. And regarding nuclear model, the nuclear excitation model is very important. So the ambiguity affects the nuclei which show up in core-collapse phase. And in core-collapse phase, nuclei around zinc 80 are very important. They show up at neutron sphere, and their weak interaction rate affects the neutronization burst and size of protoneutron stars and dynamics of core-collapse supernovae. And finally, so after shockwave formation, in shocked matter, light cluster, especially deuterons, are formed, and deuterons may affect the dynamics and neutron emission. And so recently, I'm writing a review paper, and so if you are interested in some detail of core-collapse supernova nuclear physics, please read this review paper. That's all. Thank you very much.
Thank you very much for this very nice talk. And we are open now for questions. I don't see any raised hand yet, but maybe I can start. So you had the plot when you showed luminosity of neutrinos, and it had like two peaks, the big neutrinization peak, and then this small pre-burst kind of peak on the right-hand side of this, this like tiny peak. So I can see that it's very sensitive to the electron capture rates.
Yes.
And recently there was a paper claiming that basically the height of this peak can tell us something about NSI between neutrinos and quarks. And basically the claim was that in supernova simulation, the height of this peak is insensitive to the equation of state or the changes. But I can see that from your simulation, it seems that from basically the rate of electron capture rates, it's not true anymore.
Sorry, your question is about some sensitivity to electron capture rate.
Yeah.
So
because I mainly thought that the height of the peak would be defined also by trapping of neutrinos, because you also trap depending on what is the composition of your core at that point. So if you can expand a bit more on the changes of this peak with the electron capture rates, that I would be grateful.
Yes, yes. Yes. So of course so this is not this is derived from sci-fi and so they changed the electron capture rate greatly, and so as a result some peaks are greatly changed, and so I guess so the impact of frankly speaking, so the impact of the detail of electron capture rate of these nuclei are not so influential on the result for now, but so maybe yes, so but sorry anyway so let's say yes so the electron capture rate is also of course important to determine the peak neutron luminosity, so but also they determine also the size of proto-neutron stars, and the shockwave, the energy of shockwave is changed. So in that sense, they are of course important. But so frankly speaking, compared to other ambiguity, for example, progenitor structure of the massive star, so their impact is also large, and so in that sense, so electron capture rate is one of the one of uncertainties in supernova simulation. So anyway, electron capture rates affect the size of proto-neutron star a little. Sorry.
Okay, thanks a lot. Do we have maybe more questions? Oh yeah, I see a raised hand. So I don't know the order, so I will read it just as I see it in the chat. So Wick, can you can go ahead.
Shun, that was a really nice talk. I also like this graphic a great deal. I just want to make sure I understand it. You have the two red arrows up and down. That connotes that they're anti-correlated, that as the first peak goes up, the early peak, the second peak goes down. Is that what you mean?
Mhm.
The two red arrows that appear
Yeah.
down below in the graph. In the graph, yeah. So you have one arrow at the top peak and another arrow on the deleptonization peak. Are you trying to say that as the pre-shock peak goes down, the post-shock peak goes up?
Mm-hmm.
Or are you saying something else here?
So in my talk, I talked about the peak neutrino luminosity, and of course the pre-shock peak is also changed. And so depending on the distance of our supernovae from our solar system, so we may be able to observe the pre-shock neutrinos. And so of course this information may be helpful to understand electron capture rate.
Yeah, I understand that, but it looks to me like the graphs that you've actually shown there show both peaks going up and down and correlated. I would expect them to be anti-correlated.
Mm-hmm.
That is, that the more transparent the star is prior to the core bounce, then the weaker the deleptonization peak would be.
Mm-hmm.
And I should remark this was, of course, a huge issue, that early peak in the early days of trying to understand, whether a prompt mechanism could be viable or not, because, basically the way those neutrinos get out, it's not just the electron capture, but any weak process in that early evolution of the star that allows neutrinos to occupy low energy states lead to enhanced emission. So what was discovered, it really was the failure of the prompt modulus when all the inelasticities were turned on. Mm-hmm. Then the lowest energy states in the Fermi sea that are emptying at the speed of light because the star is transparent to them, they get refilled on the same time scale. And so you have this kind of pump that manages to shed more and more electron number during the collapse phase. And that winds up leading to a smaller homologous core and a weaker shock wave, and prevented the hydrodynamic model from working. But I'm really curious about the correlations here, because it looks from the graph as though both peaks are going up and down together, but just intuitively I expect them to be anti-correlated. So I just wanted to make sure I understood the graph. It looks like from the blue curves that the more early pre-bounce neutrinos you have, then you also have more post-bounce neutrinos, which is, I find, a little surprising.
Yeah, thank you for that. Yeah.
Okay, thanks a lot. And we have another question from Zilu Li. If you can unmute yourself.
Yes. So Shun, thank you so much for your interesting talk. So maybe my question is kind of naive. So I just want to make sure that when this electron capture happens, when it matters, so we cannot assume that we still have that NSE. Is that correct? The nucleostatistical equilibrium. We cannot assume. Okay.
We can assume NSE.
Oh, so you mean that for this electron capture rate matters, so you are still assuming NSE?
Yes.
Okay. So, but I guess if NSE is assumed, why the weak interaction still matters? Because anyway, as long as we know the binding energy or the information about the nuclear models, then we can determine the component of those nucleus, right? We don't need to calculate the weak interaction if we assume NSE. So
yes. So
yeah, can you explain why this electron capture rate is still important? But yeah.
So the time scale of first law, so we can assume NSE via strong and photoelectromagnetic nuclear interactions. So and the time scale of so we can calculate this mass fraction or nuclear component. So as function of density and temperature and charge fraction. So if we set the density, temperature, and charge fraction, we can calculate this nuclear component.
Right, yes.
And weak interaction determines the evolution of charge fraction.
Okay.
Okay, so and neutrino and the time scale of neutron diffusion is longer than the dynamical time scale and strong nuclear interaction and electromagnetic nuclear interactions. So weak interaction determines the evolution of proton fraction or charge fraction. And when we set the charge fraction, we can calculate nuclear component.
I see. Okay. So I just want to verify that. So in all the calculations that is presented in your talk, you are assuming NSE. Is that correct?
Yes.
Okay. Thank you so much. Okay. Yeah, thanks. That's clear. Okay.
Thank you very much. We have a next question from Tianqi Zhao. If you can unmute yourself, please go ahead.
Yeah, thank you for the nice talk. I have a question regarding the compressibility you're talking about, the stiffness. Did you mean the stiffness is more important for the symmetric nuclear matter compressibility, or the symmetry energy, or the compressibility for pure neutron matter?
Yeah, so this your question is very important for our community. So there are many discussion about the fact is a key parameter for supernova simulations. And actually, so in this Suwasan's paper, so they performed some systematical study by changing incompressibility parameter. And so among these EOS, the symmetry energy is also different. So STOS, EOS show large symmetry energy, and there are many discussion about, but we didn't understand which is the key parameter. So compressive parameter may be also important, but so symmetry energy also affects stiffness, and sometimes symmetry energy affects the weak interaction rate. And there are many discussions. But so recently, so in conclusion, so incompressive parameter and symmetry parameter so may not be so important in supernova simulation. They are not influential on, they are not so influential on the dynamics. And so recently, Schneider showed the effective mass in scheme type interaction. So they change incompressive parameter or some other parameter systematically, and they find the effective mass is most influential on the result. This is one result. And as a group show, the entropy density may be important parameter of nuclear matter. So they affect the motion of convection. So yeah, of course we need more investigation. But recently, so these key parameter for stiffness, maybe effective mass and entropy densities.
Okay, thank you. So very quick question. Do you think the electron fraction at the center will matter to the neutrino production and thus the radius of a neutrino sphere? Are there studies about that?
Sorry, your question about.
So I'm asking the electron fraction at the center of neutron star. So in your profile, I see that the center electron fraction or the proton fraction increase in the core, right?
Yes.
Does that center electron fraction or proton fraction matters to the the neutrino radius? Like have a correlation or something?
So your question is about
so it seems your equation of state has a relatively large electron fraction at the center. Does that play a role in the neutrino the supernova simulation?
Yeah.
About how if it's success or not success. Okay, that's my suspicion. Okay, thank you anyway.
Thank you very much.
Thank you. And I think we'll have last question, and then we will still continue with the discussion. So James Latimer has a question, if you can unmute yourself.
Yes. I think that previous figure you showed shows pretty clearly that the incompressibility of symmetric matter is not important, but that the symmetry energy and or the effective mass are the two key parameters in the supernova simulations. And unfortunately, the STOS equation of state has both a different effective mass and a different set of symmetry parameters. So it's not possible to decouple that from this comparison.
Yes, you are right. So STOS and LSEOS have different effective mass and entropy densities. And so indeed, this comparison, so we should check it. And of course.
Right. Yes. Okay. Thank you for the excellent talk, by the way.
Thank you.
Okay. Yes, thank you very much for this very nice talk. And if people want to stay for the discussion, we can use Shun Furusawa for extra few minutes if he agrees. But otherwise, see you again at our next N3AS seminar in 2 weeks. Okay, I will stop recording.